Using polyatomic ions in making formulas for salts or ionic compounds. Ionic compounds are going to be composed of cations and anions. The cations are the positive ions, and they can be metals from group 1A or 2A, which will always have either a +1 or a +2 charge. Aluminum will always have a +3 charge. Zinc, silver, and cadmium ions have either a +1 or a +2 charge, as noted here. And then we have a variety of ions, of metal ions, that have variable oxidation states or variable charges. And for these, we would use Roman numerals. For example, Fe+3 would be called iron 3. And sometimes they use a parentheses and sometimes they don't. So the parentheses might not be important. We have a few positive polyions, and polyions are those which have more than one atom in them. Ammonium is an example of one of those, and that's NH4+. So that's an example of the possible cations. The anions would be nonmetal ions from the chart, and they will all end in IDE. For example, the sulfide ion in group 6. And then polyanions. Many of these are oxyanions, like sulfate, and a few others end with IDE, which means they do not end with oxygen. Hydroxide is OH-, and the name of the ion is sort of opposite the way you write it. You write the... So, when we look at using these in making formulas for compounds, here's the list of ions you should be familiar with. It's not all of them, it's many of them. And you will see, number 1, that almost every ion in here has oxygen in it. In fact, most of the ions end with oxygen. The OH ion is one that doesn't, and the ammonium ion is the only positive ion in this list, and the cyanide ion is another one that doesn't end with oxygen. Notice that every ion that ends with oxygen, every one but the ones I have arrows with, have a T in them, and they will either end with ATE or ITE. And actually the difference in ATE and ITE is the number of oxygens. Here's nitrate, starts with N, and then the ending, the A represents more oxygens than the ite does. Now, here is another list where we have ates and ites, and notice that we've got a prefix in front of some of these because we've got a total of 4 of them. So, if it is a monoatomic ion from the chart, like sulfur in group 6, which is -2, it is just sulfide. But if it has an O in it, like SO4 -2, it will be sulfate, and it's that T that tells you that there is an O there. Okay, when we use these in making formulas, for example, suppose we have calcium hypochlorite. We're going to do the same thing we've been doing in the previous compounds. We're going to write down the 2 ions, and then we're going to cross the charges. We would need 1 calcium, as we're going to cross that 1 down to the calcium, but we're going to need 2 hypochlorites, and to do that we're going to put a parenthesis around it and a 2 outside. Notice that this is different than writing that formula. In this case, the 2 would refer only to the oxygen, not to the entire group, which is what you want to do. So in a lot of ways, it's like saying I've got a calcium +2, and then I've got some negative ion that is a negative -1 ion. So I would need 2 of those X's and 1 of the calcium. But if it is a polyatomic ion, I need to use parentheses. Another example might be aluminum sulfite. So here is aluminum at +3, and then sulfite is down here, SO3 -2. Well, I'm going to have a 2 to 3 ratio. I will need 2 aluminums. I will cross the 2 down. And then I'm going to need 3 sulfite groups. Well, I'm going to write the sulfite formula, the SO3, and then I will need a subscript of 3 to follow that. So you have a worksheet that is sort of a spreadsheet that has a variety of ions with their names of the ions and the formula. Well, the neat thing about the naming is you just name the 2 ions, aluminum sulfite. That's all there is to that naming. But the formula, you have to know what the charges are to come up with the correct formula. So, good luck with the worksheet.